Okay, let's solve a numerical that is from the exam. Okay, test 1. Question 3 was exactly from the slide, right? Question 2, let's solve it. I will solve it in our own way. There is a solution available in solution manual, but let's see how we will solve it. So here we have inner and outer surfaces of a wall. Inner and outer surface, so it's a wall. Inner and outer surfaces of a wall that is 25 centimeter thick. So keep on writing what is given. So that is 25 centimeter. They are at a temperature of 27 and 44. Inner is 27, outer is 44. So inner T1, 27, outer T2, 44. So these are the temperatures which are given. During summer, the wall's outer surface exchanges heat with the surrounding environment. Okay, there is a heat exchange with the surrounding environment which has a surface temperature of 40. Yeah, so here is a bit confusing. The wall's outer surface exchanges heat with the surrounding environment which has a surface temperature of 40. So surrounding environment is 40 and whatever is surrounding surface, sky or whatever, we do not know, that is not specified, so that is also 40. This heat exchange occurs via radiation and convection. Whatever is this heat exchange between this wall and surrounding is by convection and radiation, both with the convection process taking place with ambient air at 40. So convection is with air at 40 and convection heat transfer coefficient is 8 watts per meter. So convection heat transfer coefficient is given 8 watts per meter square per degree Celsius. Additionally, the surface receives solar radiation at a rate of 150 watts per meter square. So there is solar radiation incident on that wall, and that is given as Q dot solar 150 watts per meter square. The emissivity and solar absorptivity of the outer surface. So here alpha is equal to emittance 0.8 is given. Sketch the system schematic, that is system schematic with complete labeling, and show all the thermal energies entering and leaving the chosen system or surface. So here we have not shown all the thermal energies, only Q solar is shown on that surface. The surface we should choose, of course, this one, where all the energies entering or crossing. So it means this is our surface, only surface we are choosing. So on that surface, this is the Q dot solar, there will be conduction from this point, because here you have 44, here you have 27, so the direction of conduction heat transfer will be this one. Okay, there is 44 and here you have 40, both fluid and surrounding surface is 40. So there will be a heat transfer from this surface at 44 to surrounding surface by by convection, and by radiation, because radiation data is given. Because here temperature is 44, here temperature 27, so the heat will be conducted like this. But from here to the ambient, the direction of heat transfer is from high temperature to low temperature, which is 40. Why this temperature is high? Because it is absorbing some Q solar. This air is not absorbing this Q solar. That's why the temperature here is lower than the surface. Now directions and all the energies are shown. That is our system or surface which we have chosen. Now we can write its equation and what we need to find out. That is part A. This was part A. How many marks?
Should we add a more arrow from the reflected from Q's because the sensitivity is 0.8?
Okay, if you add it, good. But here I'm saying this Q energy is incident, but how much is absorbed is actually, yes, you're right, then we should write it like this. But if you are not writing here, but you are writing here in the equation, it's fine. Okay. Otherwise, okay, if you show Q reflected also 0.2, that though it's also okay. Okay, not required, but it's fine. Okay, so this was part A, 5 marks. Right. Part B, calculate the wall's effective thermal conductivity. Okay. K of wall we have to calculate. For that we need to know how much Q conducted. Okay. So for that we have to write the energy balance on our surface. What is that surface? So for that surface, the energy balance, we know E in is equal to E out. For a surface, the energy stored is 0, steady state, no heat generation in the surface. So that means our energy balance is simply E in is equal to E out. So what is the energy entering? Entering.
Alpha.
Q dot solar, yes. Alpha into Q dot solar. That actually enters into the surface. Any other entering? No. All others are leaving. So Q conductive is leaving plus Q dot convective is leaving plus Q dot radiation is leaving. Small Q dots because area is same for every Q, same area. Even if area is given, that will cancel out. So that's why we are writing in. So now write this, that is given, what will be Q dot conductive? K dt by dx, but which dt? Now you can write minus k t1 minus t2 or k into t2 minus t1 in this direction. So k into t2 minus t1 over 25 or L. Okay. Q dot conduction plus Q dot convection H delta T T2 minus T infinity, right? Higher minus smaller plus Q dot radiative epsilon sigma T2 to the power 4 minus T surrounding to the power 4. So from here we can find out K, every other term is known. Here we can use Celsius in both these terms.
Watt meter square Kelvin, no difference?
No.
Convection.
Because convection coefficient is HA delta T. From here, what are the units of H? Watts per meter square per, what is this thing? Delta T. So whether Celsius or Kelvin, it's same. So no need to change. It's already delta T. But here, both of these must be Kelvin. If you have used Celsius here, you will definitely lose marks because this is very important. Yeah, because this will change your answer very drastically. Okay, so that's what you have to do here. Again, units, thickness, centimeter. So every other thing is in meters. That must be divided by 100 here. That is centimeter. Okay, here it must be Kelvin. Here it's up to you whether you use Kelvin for both or Celsius for both. It's up to you because that is simple delta T. Okay. So here is the solution. So answer is 0.961 thermal conductivity of that wall.
Q for conduction will be 0
Why?
because we have TM 40
Hmm.
and TS are also 40. And question
44.
is 40.
40 is the outer surface. Wall's outer surface exchanges heat with the surrounding environment, which has a surface. Surrounding has a surface. The surface temperature is 44. Inner and outer 44. Okay. So that was that question. Let's solve one more question from chapter 3, which we didn't solve in the class. Which one? This one. So now it's a sphere, not a wall. A 5-meter internal diameter spherical tank. So here is the internal diameter. So let's draw it separately by showing all the energies, etc. So here is that sphere. Show the thickness bigger so that you can show every data clearly. Here is the sphere. 5-meter internal diameter. This one. In other words, because in equations we are using radius, R1, R2. So let's show radius only. So R1 is given 2.5 meter. Okay. It's a spherical tank made up of 1.5 centimeter thick stainless steel. 1.5 centimeter. Yes. So that thickness is 1.5 centimeter. Means R2 is 2.5 plus 1.5 divided by 100 because it's centimeter. So that is our R2. Okay. And it is made up of stainless steel. Okay, of that spherical wall, 15 watts per meter per degree Celsius or Kelvin. It's same because again in the definition of K, it's delta T, right? Next, it is used to store iced water at 0 degrees Celsius. It is used to store ice water. So inside we have ice water at 0 degrees Celsius. Inside T infinity 1, you can say. Right. The tank is located in a room whose temperature is 30. So this tank is located in a room whose temperature is 30 and the walls of the room are also at 30. So T infinity 2, T infinity 1, T infinity 2, both that is 30, and T of surrounding, which we normally need for radiation heat calculation, that is also 30, both. Next, the outer surface of the tank is black. So outer surface of the sphere is black, and emissivity is given as 1. And heat transfer between the outer surface of the tank and the surrounding is by natural convection and radiation. So like radiation is not neglected. the convection heat transfer coefficient at the inner and outer surfaces of the tank are given. At the inner surface, Hi, and outer surface, Ho. Inner is 80 watts per meter square per degree Celsius, and outer is 10 watts per meter square per degree Celsius. Right? That is the data given, and we have shown it. So in the exam, you can expect again 5 marks for this one, which is not here, but that will be a part. And maybe you will be asked to draw thermal resistance network. So if you are asked to draw thermal resistance network, so maybe I say 3 marks for that one also. All right, so let's draw its thermal resistance network. Now we are starting from fluid, ending fluid or surface. Both are same here. So starting from the fluid, so first heat transfer resistance will be what? Here Hi is given. Convection. Okay, so here it is T infinity 1 and this will be T1. This will be T1, this will be T2. So from T infinity 1 to T1, it's 1 over Hi into area, inside area, HIAI of the sphere. Next, yes, it's conductive, and that is sphere. For sphere, it is R2 minus R1 divided by 4 pi K R1 R2. That is the conductive thermal resistance for sphere wall, spherical wall, from T1 to T2. Okay, next, T infinity 2, but how many resistances from here to here? Yes, 2 resistances in parallel. So that is T infinity 2, and we have convective 1 over H outside, area outside. And second is 1 over H radiative, area outside. Okay. So that is the thermal resistance network. Now we need to find out the rate of heat transfer to the ice water, because the direction of heat transfer is from high temperature to low temperature, and high temperature is here. So the direction of heat transfer is like this. Q dot, which we need to find out. And the amount of ice at 0 degrees Celsius that melts during 24-hour period. Okay, first let's calculate Q dot. How much heat is flowing from T infinity 2 to T infinity 1. So the equation will be Q dot is equal to T infinity 2 minus T infinity 1 divided by, yeah, so here you have 2 resistances in, so let's name it R1, R2, R3, R4. That will be easier. So this is R1 is equal to, that is R2 is equal to, that is R3, that is R4. So the first resistance, 2 in parallel, so it will be R3, R4 over R3 plus R4. That is equivalent resistance, parallel. It was one of the MCQ also. Plus next R2 in series, next R1 in series. Okay. Now one by one. 1 over Hi. What is R1? 1 over Hi is given. What is area? Area, inside area of the sphere is 4 pi R1 or Ri square. Okay, hi given, everything is given. R2, what is R2? R2 minus R1 over 4 pi k R1 R2, all given. Okay, so that is okay, all given, all given. Now R3 and R4, what is R3? Convective, right? 1 over HO, HO is given. What is outside area? Yeah, 4 pi R2 square. So that is also given. Now R4, it's radiative resistance 1 over HR into area. Area is clear, 4 pi R2 square. Now what about HR?
Sigma
Epsilon sigma T. Which two temperatures are there? T2 and T surrounding. So it was T plus, yes, T surrounding into T2 square plus T surrounding square. See chapter 1 if you forgot. But here now let's see what is given. Epsilon given, sigma given, T surrounding given. T2, where is T2? T2 is not given. So now we have two unknowns in this equation, Q dot. On this side, T2 is unknown. So here, what we can do, we can assume T2.
because it's black void.
Yeah, even then, black body will make change here. And nothing else, what we can do else. T2 we have to assume. And then check later. So we need to assume some appropriate value of T2 and later we can check whether it is good. So assume T2, find out everything, find out Q dot, and then we shall check whether the assumed T2 was correct or not. Okay. So what should be the appropriate assumption for T2? Look, T1 is 0, near to 0, you say T infinity 0. Outside is 30. So, yeah, that's what I want to discuss. So here we have a sphere, it's a metal sheet, very thin sheet. How much? 1.5 centimeter. 1.5 centimeter thick sphere filled with ice. So just assume if this sphere is here in this room, if you touch it, outside is 30, how it will feel? Cold, because it's metal. So it means what should be the appropriate assumption? Below 30, definitely. That's one. And higher than 0. Inside is 0. But how high? Now you said initially 10. But I would say no, assume 5. It will look more cold. It will feel more cold than 10. 10 is also okay, but then maybe you have to iterate again if initial assumption is too different from the actual one. So if you say T2, you can assume here T2 as 5 and solve it, find out Q dot. Now how to check whether this assumption was correct. Now this Q dot we have calculated from the overall T infinity 2 to T infinity 1. I can use the same Q dot for this part, only for this part. So use the same Q dot for this part only. What is this part? T2, sorry, T infinity 2 minus T2. divided by R3 plus R, sorry, not R3 plus R4, R3, R4 over R3 plus R4. Okay, and here T2 is unknown. Now Q dot, whatever you have calculated, use it here and find out T2, because here you have in the radiation resistance T2 unknown. And whatever T2 you will get, compare it with the initial assumption. If both are same, so your initial assumption was correct. Otherwise, whatever you get here, use this one to again solve it until both converges. That's how we have to do it. So if you assume initially 10, maybe the answer will come here around 6, 7. So you will do it again 2, 3 times. So now we have computers, they can do it very easily, quickly. That's the new thing in this question. All other questions are very similar, which we have solved already. But here in this particular question, one of the temperature was unknown. So that's how we can solve such problems, because under steady state, same Q dot is flowing. So we can use this Q dot for the overall or for a small part. Okay. Any question? This is part A so far. So once T2 is corrected, so whatever is the Q dot, that will be your answer. Now the answer will be in what units? Here we are using watts, watt per meter square. So the answer will be in watts. Watts means joules per second. Second part. We need to find out the amount of ice at 0 degrees Celsius that melts during 24-hour period. Now what we have calculated, amount of heat which is entering into the tank in how much time? In how much time? In 1 second. So we can find out total heat which is entering into the tank in 24 hours. So multiply this Q which we have calculated with 24 hours, 3600 seconds. This second will cancel, so we'll have answer in joules, a big value in joules. Amount of ice. We need this much heat to melt the ice at 0 degrees Celsius. When ice will be melting at 0 degrees Celsius, its temperature will not change. So what is that heat? For 1 kilogram, we know from the tables. So for 1 kilogram, this much heat is required. And actually there are this much heat, so how much kilograms? So this divided by 333.7 kilojoules per kilogram. So answer this kilojoule, this must be then divided by 1000 kilojoules. So this kilogram, you can find out kilograms of ice which will be melted. Yeah. Okay. So let's see the solution. Schematic resistance network, right? Equivalent resistance, overall Q dot, right? So now start calculating each individual resistance, right? R1, more convective outer, this is area, surface area of the sphere, or radiative. Here we have assumed T2 as 5. And here again, always remember, it's not delta T. So here temperatures must be in Kelvin. 5 plus 273, T surrounding is 30, 30 plus 273 square. It's not delta T, okay, the radiative part. So these are the resistances. All the resistances are calculated. Now use, this is equivalent resistance, okay. So this is the total resistance. Heat transfer, now we have calculated 30,581. Now we need to check T2, which we assumed. So how to check? Oh, he is not checking, he is directly calculating. Actually, his assumed value was already correct, that's why. But he will check it. Okay. So now that I already explained, this total Q will be Q dot multiplied by total time, which is 24 hours multiplied by 3600. So here is the answer in in kilojoules. Here it is joules, so you have divided by 1000 also. Yeah, after dividing with 1000 you get this answer. Okay, it's not written here, so there must be division with 1000 to have kilojoules. Okay. So then you can find out how much mass of ice is melted. How much is melted? 7,918 kilograms of ice will melt in 24 hours. So now if you want to reduce this ice melt, so it should be insulated. You can do the same problem with some insulation, right? Thick insulation. Okay, to check whether T2 was correct or not, so we are using that Q dot for this part from T2 and T infinity 2 for this part. So here H radiative, which you already calculated, in H radiative, T2 is unknown actually. Yeah, this T2, what he is doing, he is using T2 from resistance, yes. And he is calculating, okay. So it means in HR radiative, he is still using 5. But here, T2 is taken as unknown. But I think it should be unknown here also. Yeah, there will be T2 unknown with scale term and T2. Yes, that. Anyways, now he is using the same convective coefficients, and here this T2 is taken as unknown. Now it comes out to be 5.3. So initial assumption was 5, right? So he will stop here, but if it is too different, then you have to do another iteration. So he's using the same radiative heat transfer coefficient, which he used earlier with 5. And now using that 5, he is calculating T2 from this equation as an unknown, right? So if you choose, you can try it with 10. At the end, you should end up near 5. Okay. And you can easily program it. Yeah. Any question? If no question, so that's all for today's lab.